Hello everyone, welcome to episode number 33 of this Amiga 68000 programming course based on the book of Fabio Ciucci, who I personally thank for letting me stream his book. So we were doing the conditional code register flags, okay, and we arrived in lesson 8p7. That's the last one that we did. There are only two remaining from the whole course. Remember, this is a course on its own with the way it was written, and we went through it. Then we will have another lesson related to data, graphics data basically, and then we have some code which I've written myself and I've also enhanced based on what you see down here, which I will share with you. Then we'll start the Blitter. So today, for those that always wonder what the Blitter is, you're going to learn what the Blitter is. I will not go into the detail. The detail will be into the next week, because today there is not enough time to go into the detail, but I'd like to, but there isn't enough, unfortunately. So let's jump to the Amiga. And actually I'm going to use the split screen. Now in this mode things are a bit, the Amiga is a bit stretched. Everything is a bit, but at least it permits me to be able to see the code on the Amiga and the code in Visual Code, because when I'm running it I will not be seeing it again anymore, and sometimes I need the book and the Amiga, so it's not always possible. As you can see in the lower right hand corner there is the book, but of course it's impossible to read there. It's just a place where right now I have an image. Sometimes I can switch on my webcam and there will be my image there, but for me it's waste of bandwidth if I use the camera. So let's see what's going, what we will do. Jumping back again a little bit to the book, just to show the exercises book. Okay, so we are going to do this exercise. Okay, the book, for those that may be joined, is in Italian, but I am translating it via the streams and explaining it bit by bit, and I'm showing you how to code in 68000. Assembly is assembly. It doesn't matter which language you speak. You just need to follow the code. So we have, I'm just going to show we have two portions of this code. The first one, we're adding two 64-bit numbers, okay, and we see what happens when you do an add and then ADX. And then we have another two 64-bit numbers, and we do the same. We are doing it to show you how the flags behave. So let's start with the first one, okay, the first bit. Back to the Amiga. So give me a second to switch my screen, because I didn't do that, which is stupid. And now we display the registers and execute the first instruction. So this is the low word of the 64-bit number. Okay, so we are moving the B1111 for 000 into the 0, okay? And you can see that the 0 got that value. Then you are moving the double twos, the 8 twos into D1. So you can see the 0 and the 1 already populated. Then, so that is the first number. Remember, the low word is in the 0, the high word is in the 2, in the 1. We do the same with the next 64-bit number. This is the low word, and this is the high word. Now we're going to do the first addition. Okay, and notice we are using add, not ADX, because we are the sequence to do an addition of a 64-bit number is by doing first add and then you need to do ADX, and I will explain why in a second. When you execute it, you can see that we have the result in the 2, but we have the overflow flag set. That means the number is too big to fit in the 2, and it always also tells us that the carry flag was set and the X bit, extended bit, was also set. Hence, now we need to use ADX, which is the next instruction that we're going to execute. And when we execute this, okay, you can see that we have the correct answer, because the high word has got the CD, 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 CE, and then the number, the 3345. So that is the summation of the two long words. So the summation of a 64-bit number. Now we're going to do the same thing, but this time the high word of the 64-bit number is at 0. Okay, so we move the low word into the 0, and then we move the high word into the 1, and you see that it's 0. Notice that the 0 flag is set because we moved that 0 into a data register. Then we move the low word again of the second 64-bit number, and we move the 0 into the 3. Notice that the Z flag was set. Okay, it is here, the Z flag. We're going to do an add of these two numbers. Okay, the result of them is not at 0, hence the 0 flag will not be set. Okay, then we're going to add the high word of these two 64-bit numbers, but remember, both of them has got a 0 in it. As you can see, okay, the result obviously is 0, but the add X instruction does not set the 0 flag, because the add X doesn't affect the X or C or the carry flag. Okay, so it leaves, it doesn't affect the 0 flag, sorry. So it leaves things as they are. So you need to be careful of this when doing what do you mean? I mean, a 64-bit number, you always have to split it because it doesn't fit in a 32-bit address. The registers can only have 32-bit numbers, so you need to split it. He could have done the high word here and the low word here. He did the opposite way around, which I found strange, to be honest, because the 68,000, normally the high word is the first one and the low word is the second one. But he did it that way. It doesn't matter in this case because we're working with 32-bit numbers. But visually, for me, I have to say that I would have preferred that he swapped them. But it doesn't really matter. The order of the registers. In what sense? I mean, we are moving a low word into the 0, a high word into the 1. You wanted to say you move the low word, the high word into the 0 and the low word into the 1. That's what you mean? You could have done that. It would still work. Of course, given that you yeah, it will work. Yes, if that's what you meant, it will work. So no issue there for sure. Okay, so now we're going to continue. And remember, there's a second, sorry, I just already forgot that we did the second part of it. We did the second part of it that was at 0. This is what you need to really, because, okay, you learned how to add two 32-bit numbers, two 64-bit numbers together. But what you really need to take from all this is the add x. Add x does not affect the 0 flag, okay? It doesn't change it if the result is 0. That was that could be a pitfall that maybe some people will fall in, but I doubt many do 64-bit arithmetic, so yeah, it's a very rare thing that we might see. So that was, as far as I know, example 8.1. Let's do example 8p91. So I'm just going to show you what we have here, okay? And I'm going to go to the visual code, okay? So we're going to explain the difference between logical shift left, logical shift right, and arithmetic shift right, okay? And also the same thing for logical shift left and arithmetic shift left. What is the difference between all these and what do they do? So the first part, I'm just going to cover this part right now. Both of them do a division, okay? When you're shifting bits to the right, you are dividing by 2. Okay, so that's the first thing. The number gets divided. The second thing that you need to know is that LSR always treats the number as a positive number. Okay, ASR treats the number as 2's complement. Okay, so the results might be a bit different. Okay, just to keep that in mind. The second part, LSL and ASL, okay, both of them do a multiplication. When we are shifting bits to the right, to the left, then we are doing a multiplication. So LSL treats numbers as positive. ASL treats number as 2's complement, but it depends on the mode that we are working. It can also work with positive numbers, but you need to be careful still, and I will explain while we're doing the example. So let's jump to the split screen and show you the Amiga executing this example. Oh. So, okay. So we are moving, okay, a number which is C003 hex into the 0. Now, it is a positive number, but in 2's complement, that is a negative number because it's higher than 7999. Okay, and remember, we're working on words, not on long words here. Okay, the same number, we moved it into the 1. Okay, so we're going to see that being moved into the 1 now when I press K. Now we're going to do the first LSR. What's going to happen? So if we have C003, if we are going to divide it, it should become half of that. And executing it, you will see that we have 6001 in the lower of the 0. Okay, remember we're working with words, so what is in the 0 right now, the 0111, it's irrelevant. We are not using that. So that is the first part. We got the correct answer when we divided the number using LSR. Now we're going to do arithmetic shift right, okay? And notice what's going to happen here. So, okay. Now, the result is E001, okay? So, as you can see, the number was treated as a 2's complement number. And one would expect the number to be 6001, but it's not, because it was considered as a minus whatever C001 is, okay? Hence, the result of the division is E001, okay? In 2's complement, the result is correct, okay? In 2's complement, the result is correct, but if we thought that this will handle positive numbers, then we are mistaken here. So just keep that in mind. LSR and ASR, what are the pitfalls when we're doing division? LSR treats numbers as positive. ASR treats numbers as 2's complement. So if we are working with 2's complement, we need to use ASR. If we are not working with 2's complement, we need to use LSR. We continue. Let me scroll the screen a bit. And we continue with the our examples. So, okay. And we moved 6000 into the 0. Now we're going to move it into the 1. And now we're going to do the logical shift left. So the 6000 is multiplied by 2. Remember, shifting by 1 bit to the left is multiplying by 2. So the number becomes C000, which we know that is correct because we multiplied it by 2, and that is the right answer. Please note that the N flag was set to indicate that this number has become a negative number if we are working with negative numbers, but we were not. The next one, arithmetic shift left. So ASR always interprets its numbers as 2's complement. Multiplication, okay, of the number is C000. Ah, yeah, yeah. Ozzy, I saw the your last part of the 68,000 pitfalls. Yes. Uh, yes, this is the last part, and we will start the Blitter basically today. So, in 2's complement, the answer is not correct. Okay? So, keep that in mind. When we shift it to the left, we got C000, okay? But the answer is not correct in 2's complement. And notice what happens in the flags. We have the negative flag and we have the V flag indicating, hey, yes, I tried to, the CPU is telling us, I tried to treat this number as 2's complement, but I got an overflow. So we don't have the correct value there. And that is why the V flag is there. So don't be fooled thinking that C000 is correct. It's not. So please keep this in mind. Remember, logical shift left or right work with positive numbers. Arithmetic shift right, arithmetic shift left work in 2's complement. So be careful when choosing these instructions. Let me... I think yesterday I skipped this one. I'm not sure, but I'm just going to do it. I'm not sure if I skipped it, but I'm going to do it because it was a mistake if I skipped it. So 9B1. And for a moment, I'm just going to come to the Amiga, to the my visual code. We have these three instructions. We have seen these many times, but we change how we test for the Fabio changed how we test for bit 6 of the BFE 001. Okay, before we were doing test TST bit test. Okay, we are doing this one, bit test hash 6 comma D2. Now we're going to do an AND. Why we're doing an AND? It's another way of doing it. So notice this is another way of testing for the mouse button. In other places, okay, he shows us that instead, if we use the branch on plus, we can gain an instruction in certain examples that we did in the past. So here, let me remember which example. So this I cannot execute them, okay? So bear with me, I just can read. He says that in some examples where we use this pattern, okay, this one is where we were moving the sprite, okay? We can now improve it by using BLO and BPL. So branch on plus and branch on, I forgot what it means right now. So we branch on low, this is, okay, lower basically than the number. So by using these two instructions, we actually saved some instructions if we had to compare them to what we had before. That is all. This is more than a pitfall, it's more how we can save instructions. So maybe we were using branch on carry set or something like that, and you can actually replace it with branch on low or branch on plus. That is all. So here he's just showing us pitfall of we might not see how we can save instructions basically, nothing else. We return back to the book. So this example 9b_1, I cannot execute it on the Amiga because it's actually full of comments and there's nothing to execute. Here is waiting for mouse, so nothing that you will see. You cannot see the flags basically, and it will never exit because it's waiting for me to press the mouse and the computer will not let me basically. But let's return to the book. Come on. Okay, so we have done, okay, we have done all these. We have done also 9b1, okay, and we have arrived to this paragraph. Now I'm just going to say some things here, okay? Please note, when this book was written, it was in 1995, I believe. I mean, it started, the first part was published in 1994, but this part where we are is in 1995. Now, at that time, okay, Kefren's or Kefcon, okay, Kefren's IFF converter was the most famous one, okay? In today's world, there are a lot better than Kefcon. And I am not using Kefcon because I don't think you should use Kefcon, because Kefcon will work on an Amiga 500, but will give you lots of problems on higher machines, okay? Hence, I use AGA to IFF, which I will show in a minute. But what this paragraph is telling us is, so far we have had an image, but we populated the colors manually. We haven't read the colors from the image, okay? And we were never saving the image with the colors, so the colors were never attached to the image. But now he's telling us, or he's going to show us a way of how we should save an image, and also how we can attach color to it, so that when we load it, we will have also the color, read the color from the image, and okay, and populate our copy list. That is what he's explaining here. Now, you can either have it as a file, as we have here, okay? In the file, there is also the color, okay? That's why he indicated with the C, okay? That color is also at the end of the image. Or you can also add them at the end if you have multiple images, let's say. You can have them at the end after the image and then switch between one image and the other. In the example that we're going to see, the colors are behind the image. There's only one image, and hence there's only one include with the colors there. But first, let's switch to the Amiga. I'm going to show you the IFF converter. So I use this one that you see here, the AGA2 IFF2. And on the Amiga, you should really use this one. To be fair, you are safe like this, you won't have issues. It's always friendly, basically. Given that I haven't done something wrong. There it is. Okay, so you load an image. Okay, this we all know. Okay, so I'm just going to go to volumes, my data, some GFX data. I don't know if there's a logo that I can use. Okay, let's go for this one. I mean, I don't know which one. There you go. So we have a Phase 101 logo here. Okay, image. Now, we have loaded it, and we have loaded an IFF ILBM image. However, for our assembly, okay, we need to convert this into RAW. So we have various options here: RAW standard, RAW interlaced, no picture data, copy list, as a sprite, mask 1, unpack chunky. There's lots of options, but we are going to do raw standard. That's what we need for our assembly program to include. Now, the default is not to include colors, but then you have another option. I'm just going to show it again because I was too fast. The default is not to show colors. Okay, but you can change this and either include the colors before the image, but normally, and this is what we normally do, they go behind the image at the bottom. So first we have the image, we have the bit planes of the image, and then we have the colors. This is how we need to save an image as raw with the colors. Okay, so that's the first thing. Now we're going to go back to the Amiga. So this is how to save, basically, for importing an image into our assembly program. I'm just going to close all windows because I don't like having too many windows open. And I'm just going to bring as in Pro again. So this is the example that Fabio is telling us to load. Now I'm going to go quickly to it because I basically already explained everything, but I'm just going to show you, okay, that here we have the include bin with our image, and just in the title, so we know what we've done, we have an image and the color. Okay, so we're saying how many colors and that we have included it, and it's raw. Okay, when we initialize the bit planes, okay, so we have had this routine 1,000,000 times. We've seen it. We are initializing 4 bit planes and we are loading, okay, we are setting the bit plane pointers using this routine. So that did not change. Okay, it's still the same. But once we have finished doing this and we've set up the pointers for the bit plane, now we need to set the colors, and that's the next thing that we do. So basically, where the logo is, we add 40 times 84, how big the logo is that he's trying to download, to load. It is for bit plane, so that is the size. Okay, so we need to skip that, so we get the address into 80. Then we get the address pointer where we have our colors in our copy list, and we start. It's 16 colors as we saw. It's an image with 4-bit planes, okay? And we start a loop of updating the color in the copy list, and that is basically, those are the pointers and this is the color. Okay, notice that the color, we initialize them by 0, okay, all of them. Once we hit the mouse button, they will be shown, they will be loaded from the image and shown to the screen, and I'm going to show you the example. So there is, the image is already loaded there, but we do not see it. The reason why is all the values, all the colors are 0. Once I press the mouse button, boom, the colors are loaded and the logo appears. This is to show that with the image, we also had the colors that we read and we populated. We read them and we stored them into our copy list and populated the copy list. That's basically it for this example. Now, I'm going to show, the next example is not documented, but I'm going to show it. Not this one, sorry. Now, Fabio wanted to show us how we can detect certain things on the hardware, okay? And he wrote this small little program, okay? Of course, I added phase 101 there, it wasn't there, and the 1.01, but the rest is what Fabio did. So we are testing the hardware that we are running on, and we are seeing that we have a processor 68030, mass coprocessor there isn't. We are running an AGA chipset, and there is, he writes, great, an AGA machine, phase 101 rules that I added. Now, this program, I took this program and I enhanced it, because there it doesn't tell me how much memory there is, and it doesn't tell me how much chip I have and how much fast mem I have. Also, it doesn't tell me which kickstart I am running on. So I took this program, modified it completely. Basically, I left the layout of it, but the program is completely modified, which I will show, and created like a test program that I run. Let's say I have a game that can run in AGA and in OCS. I can test before I run the program which one to load or which mode to load in, because of the program that I wrote, okay? However, the test of Fabio was an initial thing. There are things in this program that are outside the scope of this book. The reason why is there are system calls, so you need to know what the system calls do. But I will show them to you, but I will not go into the detail except giving a basic overview of them. So, in the first part, okay, as you can see here, we are setting the bit plane pointers. Here the text is in Italian, okay, because of course this was written by Fabio, but in my version everything is in English. I'm going to show my version too, to show you the differences, but I just want to cover certain things that Fabio did, because also I think it's fair. So here, okay, he's setting up the bit plane pointers, okay. Then look at these 3 routines: CPU detect, FPU detect, and AGA detect. So you can guess what they do. The first one detects the CPU, the second one detects the FPU, and the third one detects the AGA. When these routines are executed, they populate a certain screen, which I'm going to show you, which is this screen. and they populate by where these labels are. They fill in the blanks. So they're filling in here, they're filling in the two numbers for the processor, the FPU type and chipset. Now, my version does more than this. For example, CPU type, I can detect if it's an FPGA or not. FPU type, it tells you that it is found and not found. In my case, it tells you which FPU you have. Chipset, it tells you on which chipset you are running, which Fabio does, but only says AGA and normal and nothing else. Mine goes to the level of what it is. And same with Kickstart, it tells you which Kickstart you are running. I have all the versions of the Kickstarts to test against till Kickstart 3.2. Okay, above 3.2, I haven't done any tests, because above 3.2 they are not really Kickstarts that are Amiga standard. I mean, Amiga, you know, that we can have on our Amigas. And so on. So the routines, okay, I'm just going to show CPU detect. Okay, CPU detect, you need to know a certain thing. Okay, if you have Kickstart 1.3, it's not able to detect 68030 or 68040. Okay, so that's the first thing. But if you have Kickstart 2.0 or above, then it is a good indication that you can have a 68030 or 40. So when you think that you have a 68040 or 68030, then you check to make sure that you have a Kickstart higher than 2.0, basically, because the 1.3 cannot tell you that it is a 68030 or 40. And here is, I mean, he's testing a certain place in memory, okay, from in the exec base for this bit, okay, and each bit that is set, it indicates which CPU we have set. As I said, this is out of the scope of this course. It's Amiga libraries, it's Amiga OS. We do not program the OS. However, it is a good indication, okay? That's why I like this program, why I liked it. This program is a good indication of how to use the Amiga OS for your advantage, okay, when you are coding the hardware, as he does here. The same thing he does with FPU detect, okay, and look, he just writes found, okay. My routine is more than that, because I do not write text like this. I have a proper message to display. He just injects those words directly into the place, which for a quick thing, it is good, don't get me wrong. And the same in this part where it is AGA or not. This part, okay, here, this is the print routine. This is the print routine that we have been using since chapter 4, okay? This is how we write to the screen using the Amiga hardware. So this one has not changed, okay? It's still the same. We just have a font, we read which ASCII character we want to display, and we read the bitmap for that font and display it on our screen. That's what it does. I'm just going to show my program, and I also show you the differences. Actually, let me run this once more so that you can see the difference. So just keep in your head this image, okay? Here. Now we're going to exit and read my program. So I need to go, unfortunately, quite a bit further. So this is my version of the same program, but enhanced, as you're going to see. So as you can see, it tells you exactly how much memory I have total, how much chip mem I have, how much fast mem I have, and what version of Kickstart I am running on. To display the numbers on the screen, I had to write a routine that converts hex to decimal. The reason being is that the OS returns that number in hex. So I will show you that, but that is an extra part that I had to do. Plus, as I said, I have all kickstarts. So I have like a database of all kickstarts, which I got from Wikipedia, I believe. And depending on a number that is returned in the OS, that number reflects to what kickstart you have, which I will show you also. Same thing for the MESCO processor. Here I do not have a MESCO processor, but it's able to detect whether it's 6881 or 6882, or whether it's built into the CPU or not. And same for graphic chipset, it's able to say OCS, ECS, and AGA. So please note that the source of this code is available on Patreon to the supporters of Patreon. I made this, I did not make this source public, but I shared it with all my supporters on Patreon. So, which I think it's fair. Here I start similar to him. Okay, I initialize the bit planes, but then I have my detection routines. Okay, you are going to see, okay, that I am able, it's disabled because I did not, I'm not going to comment on it, but I had to disable this. Let's say a certain, it was brought to my attention not to write FPGA, okay, because somebody might get offended saying FPGA. So I remarked that. I hope I worded it correctly. But if you run Mister for example, or Mystica, you'll get FPGA. The OS also indicates an FPGA for something else. It's how the Amiga OS was written. I'm referring to if you have OS 3.2, because you need OS 3.2 to be able to detect whether you are running on FPGA or not. 3.1 is not able to do that. So right now I have 3.1 here, and I remarked it. but it would have returned, it would not tell me that. Okay, so as you can see, okay, my way of writing is different. You're seeing it in a string here, but it's a different way of the way Fabio was pushing it directly. I am not, and you can see it better into the FPU detection, I think, or the let me see. Yeah, FPU detection. Look, I'm writing a string and then copying this string into this screen. So I have a like a copying process also, not just directly to the screen, as Fabio is doing using the instructions demove.long, because I wanted to move something that is longer. So the same thing is for FPU. Okay, you can see that it's able to tell you that if you have a 68040, which has an FPU built in, it will tell you, hey, it's there, same as for 68060. So that's for FPU. And then for chipset, it's able to tell you OCS, ECS, and AGA. And now is for the RAM. And it's able to, once it reads from memory, it converts the number to decimal and then displays that number. That's what I'm doing here. So read, convert the number, display it. Read, read, convert the number, display it, and continues like that 3 times because I have total, chip, and fast. This is the conversion routine that converts hexadecimal to decimal. That's the table, power of tens, basically, because I wanted to support the maximum number possible that the OS can return. And it's funny enough, it can return a number as big as this one. So 10 digits, basically. So I had to do a huge check, a huge conversion, let's put it this way. And then here is the routine that checks the kickstarts, okay? And you're going to see the table. See, the OS returns this number, but this number, you need to convert it into the actual kickstart version. And as you know, as you can see, I have to kickstart 3.2. The print routine is basically the same that we had before. I believe I did not modify this. I just recommented it with in English instead in Italian, but I left everything the same. The screen here, I am not injecting directly to it. As you can see, I wrote garbage, for example, here where total mem decimal, I wrote garbage. Is just to show that I will write there, but actually I can write a long thing. Unfortunately, you're seeing the tabulation wrong because I'm using the Amiga, but if I had to display this code in Visual Code, it would display better. Tabulation I had is 4 tabs, and I think by default, as in Pro, is set to 8. So that's why you are seeing the tabulation wrong. Yeah, and the rest is the same like Fabio had, nothing else. That's the code that I shared on Patreon. Now, I'm just going to jump back to the book. I just have one final note, okay, on chapter 8. Fabio saying, okay, you need to go and read the Amiga hardware reference manual, okay? You need to read that book, besides this book. Also, he's saying you need to read a book related to the 68000, and here he gives 3 books by Motorola, okay? Actually, 2 of them are Motorola, I believe. This one is not. Anyway, about the 68000. However, he also, for those that understand Italian, there's another book that he wrote about the 68000, which is a text file actually. But if you think that you can go on Google and translate it, you are very wrong, because the book is very big. So instead of reading these 3, if you're Italian, you have the choice of reading the book that he wrote himself, Fabio. I suggest that you read one of these books, because Motorola, the one that it has about the processors, okay, which covers till 68040, I believe, which is this one. At least the one that I have is this one. Programming the programming the Motorola 6804 from 68000 till 40 is quite good, and the pitfalls that we covered here, because these were all pitfalls, okay, of that we will see using the conditional code registers, are all covered there and more. These are the most common ones that we fall in. Hence, after this, we have arrived to, as you can see, coming up, chapter 9, Blitter. So we're going to talk about the Blitter from now on. There are 2 long chapters, okay? If chapter 8 took me 3 months to finish, I can tell you Blitter is going to take me a lot more, because it is twice the size of chapter 8. It's 2 chapters. 1 chapter is as long as chapter 8. So expect lots of things that we need to do and cover using the Blitter. As I said before, the book is like divided in 2. Chapter 1 to chapter 7 is like for beginners, let's put it this way, or beginning stuff, but it doesn't have the Blitter in it, okay? You can still write games not using the Blitter, but simple games I'm talking about, okay? Which eventually I'm preparing a course, simple one, of writing a small game using what we have covered, chapter 1 till chapter 7. I will not cover the Blitter. I will not do the Blitter in my game. I will not use Blitter in my game, to show you that you can write games using the first 7 chapters of the book. And it's an excuse if you say you cannot write a game because you don't know the Blitter. Now, Fabio starts with something which I have to say he is right. And even today, 30 years later, he is still right. There are lots of people, okay, that know that the Amiga has a Blitter, and that this Blitter is an amazing chip. But few people really know what it really does. So we're going to explain that for those that are interested in knowing what the Blitter really is. This is the same thing like when I did the chapter of the copper. Lots of people have heard about the copper, but few people know what the copper really does. Hence, why you need to pay attention, let's put it this way. joking apart, but it's true. I mean, this problem is still exists. Sometimes I still hear people talking about Blitter and they simply don't know what they are saying. Okay, so what the Blitter does can all be done by the CPU. So that's the first shock for today's, you know, in modern world, all the Blitter can do can be done with the CPU, but not 35 years ago when the Amiga was released. At that time, PCs, okay, talking about 386, 286, 386, 486, did not really have graphic cards, okay? I mean, I'm talking till, let's say, EGA, sorry, okay? Because VGA, then it started to be a bit... The Amiga at 7 megahertz, okay, with a 68,000 CPU, okay, you can see it, he's saying it here, okay, so I'm not inventing, and I do remember it well also. At 7 megahertz, when these worked at 2 megahertz or something, sorry, not 2 megahertz, at, I forgot how much, but quite a high number, was able to do better than them. And the reason is because it had the Blitter. Same reason why it was able to do better than the PC with sound, because it had Paola, the chip that produces sound. The PC had none. So these were things that made the Amiga special in a way. Also, it had the copper, so something that the PC did not have. However, in today's world, as I was saying, everything that the copper does can be done by the CPU. In today's world, on the Amiga, if you have a CPU above 68020, the CPU can do better than the Blitter. Okay? So, normally, and I've heard this many times from demo coders, either they use the Blitter with the CPU or they use the CPU for when you are using a higher spec Amiga, because the Blitter did not continue to be enhanced by Commodore because Commodore left us basically, and because it wasn't not enhanced anymore, then unfortunately CPUs superseded it, and the CPUs superseded also because Motorola continued to develop at a later date. They stopped, but continued to develop the 68000, while Commodore was not there anymore. So let's see what else Fabio said in relation to the Blitter. Yes, one important note that I need to make here. The book so far, we are in chapter 9, till I say so, okay? We are always thinking of using the 68000. The other processors, 68010, 68020, etc., do not exist yet, okay? Everything that I am teaching, okay, or trying to show you is with the 68000. So there's a chapter dedicated to the other CPUs, okay? Starting from the 68010 to 68040. 60, of course, was not there. So it's not discussed when the book was released. But till 68040, it is covered, and we will be talking and cover what we can do with those CPU at a later date. So far, everything is with 68000. Yes, yeah, the Blitter could have been increased significantly, but it was never done, unfortunately. But yeah. So still, please still think of an Amiga 500. Don't think of an Amiga 1200. In fact, we haven't covered AGA. AGA comes at a later stage in the book. Okay, so let's not go there. We are 68,000 using OCS or ECS, nothing else. So that's the first thing that we need to be clear. So the Blitter is always fast in this configuration than the CPU. Okay. What does Blitter stand for? Blitter stands for block image transfer. That is the meaning of Blitter. Okay. Now the double T, I do not know where it comes from, but there is a double T in Blitter. However, if you see the capital letters here, there is only one T. But that's the meaning of Blitter. In short explanation by what we mean by, because I'll say, okay, I said what Blitter is, and I said what is the meaning of it, block image transfer, what it actually does, in simple terms, okay, it does more than what I'm going to say, but in simple terms, it is able to copy from one place in memory to somewhere else very fast, that the CPU cannot do. That is the main function of the Blitter. It has others, but this is what made the Blitter so important. The PC did not have this. It was not able to do, okay, to have the speed in copying with all the Intel CPUs that it had, okay, and I used to work for Intel, so I am I was in Intel research, to be honest. Intel was not able to reach the speed that Blitter was able to handle. So this was something phenomenal at that time. At 7 megahertz, how you can have a chip copying a block of memory from one place to another at such speed. And that's why it made the Amiga special. So in reality, what we are saying is we are just doing block image copying. It's one aspect of the Blitter, but it can do other things like filling, like line drawing, etc. But that is something. Yes, it's always running in parallel with the CPU. I have to correct you in a way, if you don't mind, Ozzy. It runs in parallel with the CPU to a certain extent. The Blitter can take over the CPU and can tell the CPU, hey, go away, or I want all the cycles for myself. It's able to do that. Also, you can take advantage of having the CPU and the Blitter doing two things at the same time. But the limitation of the Blitter is that it can only work on a certain amount of memory, while the CPU can see all the memory. So that's another aspect of it. And when it comes to chip mem, that is where the Blitter can work. The CPU can work and a lot fast in fast mem, while if the CPU tries to work in chip mem, normally the CPU is limited. Also, at a later time, you are going to hear about something called the Blitter nasty. Okay, if you enable that bit, basically the Blitter will start stealing cycles from the CPU, and you can end up just having no CPU for a short period of time, let's say, while the Blitter is doing what it needs to. But I do not want to go there, and I do not want to go why the Apollo team doesn't make a Blitter or things like that. But I believe you're correct. I like the Vampire personally, especially version 4. And the reason why I like version 4 is because of the enhancements that it has. I do not, if I wanted an accelerated Amiga, okay, I do not see the Vampire, with all the respect to the Apollo team here. But if I want an enhanced Amiga, something that did not exist but now we can have, like the same project that is happening with the Mega 65, where you have the Commodore 64 and now there is the Mega 65, which can do a lot more things. Basically, it has what is called the VIC-4, okay? Then yes, I like that. Okay, so it is an improved version. Yes, the Blitter, yes, it is a re-implementation in V4, but it's just the same one. What I was referring is to the actual FPGA. I mean, what is able to do the V4 in total. In terms of Blitter, I think it's still the same. No compatibility with what there was before. My understanding of that, but I mean, I don't know. Nowadays, you don't need Blitter because the CPU is a lot faster, and the 68080 is a lot faster than what the Blitter can do. So you might as well use the CPU, like what the PC does. I just got distracted. I'm just going to continue. My yeah, I mean, yeah. If I personally wanted a faster, just Amiga, accelerated Amiga, maybe I wouldn't go for the Apollo, for the Vampire. But if I wanted something new or enhanced or better, definitely I will go for the Vampire. I think it's the best one around. I'm too much of an old school Aussie. So I like my Amigas the way they were born. In fact, I don't think even I have only one accelerated, which is my A500, which with a GVP, okay, which has an 68030 processor, which attaches to the Amiga 500, which is the A530 GVP. So and it has 8 megs of RAM or something like that. It's the only thing. When I want, I can remove the just slide it off, and my Amiga becomes an Amiga 500 as it was when I bought it. So even my A1200 or my A600, they are virgin in a way. They have a hard disk, but I never accelerated them, because when I code on them, or if I code on them, because I use the emulator, but I do code sometimes. I mean, especially on the A1200, I like coding on the A1200. I prefer the machine as it was originally. Also, I have to admit, most software tends to break after, not most, some of the software, I don't want to say most, because it's not fair. Some of the software after 68030 breaks, so I just prefer using the standard Amiga, and if I have to accelerate, then go for the vampire, which I don't have, by the way. I'm not making an advert for the vampire. I just like to have it, but I cannot afford it right now, I have to say. Anyway, the Amiga, an Amiga image, okay, a picture on the Amiga, okay, is just an image in memory, as you saw, okay. For the Blitter, working on an image in a block of memory where there's an image or there is code, it doesn't care. It's just manipulating memory, okay? So keep that in mind. And as I said, the Blitter can only operate in chip mem. Okay. Now, when I did chapter 8, I said there is a DMA for the Blitter. The Blitter has got DMA, but I didn't go into the detail of the Blitter because it still had to come. Now, in reality, the Blitter has 4 DMA channels, and these channels are called A, B, C, D. Okay, very easy. However, 3 are reading and 1 is writing. Okay, so 3 channels, 3 DMA channels can read from memory, and 1 we can write. We can use all 3 channels together, we can use 2 channels together, or we can use 1 channel together for reading. Okay, but we need the destination always. The amount that we read, let's say if we read 10 long words, is how much we write. It doesn't vary, okay? And the Blitter works in words, okay? So some basic simple rules right now, but keep that in mind. It has 4 DMA channels, 3 read, 1 write. There is 1 length, and what we read, the length of what we read is the length of what we write. So, simple rule. So, when in chapter 8 I said we have 9 DMA channels, I forgot how many, but whatever that number is, now you have to add 3 more, okay, to that number. Because actually I just said that there is 1 DMA channel for the Blitter, but actually there are 4. So the Amiga had a lot of DMA channels, something that at the PC at the time did not have. I believe I didn't even have 1, because I remember at school we were covering 8086 or 8088, I remember, and the IBM PC, and it had no DMAs as far as I know. Somebody can correct me on this, but yeah. So keep in mind that the Blitter works on words. That's very important, okay? Now, when the Blitter is doing an operation, okay, using register A or AB or AC or whatever, and D, that when it is doing something, okay, it's executing some instructions that we tell it to do, that means the Blitter is doing a blit. That is what the word blit means. We're doing the Blitter is on and it's doing a blit. It's running its course, okay? Copying from one place to another, etc. Now, we have 4 simple steps, okay? These are very simple, very high level, what I'm going to say here. But it gives us an indication of what we need to do to have the Blitter running, okay? Here is what we need to do a blit, okay? We have to decide which channels, which DMA channels we need to use. So A, for example, and D. Okay. Then I will cover this. Step 2, I will cover it at a later time. But which operation you want to perform when doing the blit? It's a copy, but how you want to copy? Do you want to do something on it, etc., etc.? It's an operation, okay? Then you have to set the DMA channels where you want to start, okay, somewhere in memory, and you need to tell it where it needs to copy to. So basically set the reading channels and the writing channels, or channel, actually, not channels, because there's only one. Then last step, step 4, you need to tell it how many words you want to read. That is the blitter in simple terms when you want to do a blit. And remember, everything is in words. I'm repeating this so that it gets into your head. As I said, note that the amount of data he's repeating it in this paragraph, so I'm reading and I'm saying it again. Note that the amount of data read is the same for all channels. So just because we have 3 channels, you cannot also manipulate how much each channel read. They all read the same length. And you also write the same length. The way the Blitter registers are set up, okay, they are, as you know, all registers, OCS and AGA registers, okay, the chipset registers, they are 16-bit. But the way they have done them, okay, sequentially, you can write to them, instead of a word, you can write to them as a long word. We have already used this technique when we were setting the blit plane pointers, okay, here, and the copper, the jump, where we're setting the copper. Okay, so we have already used this method. We will see it at a later time, basically. Now, here is the first exception to when we want to start writing to the blitter. Before we write to the blitter registers, we need to make sure that the blitter is not being used. This is very important. You need to make a check that the blitter is not being used. Why? Because if you start telling the blitter, hey, I want to start copying from here, from this source address to this destination address, you are affecting the blitter, you are changing the operation of the blitter that is carrying right now in this moment. Hence, you need to make sure that the blitter is not active, is not doing a blit. If you do so, okay, I mean, we all like miracles, no? But it depends what type of miracle. You get the miracle of the guru, okay? So most of the time you get that. Or the Amiga get confused completely. So it's up to you if you want to experience it. I think we've seen it enough. Okay. To check if the blitter is doing something, we read register 2 of the chipset, which is DFF 002, which is DMA con R. Okay, you test bit 6, and if bit 6 is, you know, has finished, it's not the blitter has finished, then we know that the blitter has finished. If not, we continue the test till it finishes. Okay, I'm going to show you the registers. Give me a second. We are going to go in the make on R. We are testing this bit. Okay, and the reason why I showed it to you, because it says bit 6, but bit 6 of the high byte of the word. Okay, so I'm just going to give another example, okay, because you can easily think we are talking about this, but this is the blitter enable. This is when the blitter is busy. Okay, so, and it's a read-only bit. So when the blitter is busy, this will be a 1. Once it's 0, it's ready. Okay, so this is what we need to test for, bit 14. Just to show it to you better, I'm just going to go back to the book. On the Amiga hardware manual, which Fabio told you to read, okay, we have the same register, and I divided it. As you can see, here we have the low byte, and this is the high byte of the word, okay, and we are testing bit 6, okay, just to be clear what we are testing for. So don't confuse it, we are testing this one, but this one. This note is not in the book, but I thought some of you might fall for it, so that's why I'm indicating it. Now, that's the first thing that I said you need to check, that the blitter is not being used. But to make things worse, there was a bug in the first Amigas that were released. I believe this bug is in the A1000, but I do not know which ones, but it has a bug. The Agnes has got a bug. And this bug is that when you read it the first time, you can get a false number, you know, a false value. Hence, you need to read it twice. Okay, we will see later how to do this, but this is something that you need to know. Testing for the blitter the first time, you need to run it twice. So this is where I arrived yesterday in the Italian stream. You know that I keep them in sync, so where I finish with the Italian stream, I finish with the English stream. So basically we finished, I finished talking about the blitter, but I haven't scratched the surface yet. Okay, I spoke a lot today. However, I can promise you that next time you will see the blitter in action. Okay, it's not like chapter 8 where I talked a lot and then only at the end you saw a lot of things. This one, this chapter, you'll start seeing things as we progress. Okay, so next weekend you will see how we actually write code and control the blitter. There are, just to give you a heads up, the first few examples are just how we should set up for the blitter. Then we actually start seeing things happening with the blitter. So keep in mind that there might be examples, okay, that is code that when you run nothing happens, but actually it's code that we need to have so that we set the blitter, and we need to understand that. So it is something that I will explain again next week, but just to make you aware that if you see blank screen doesn't mean if some of you go and start running the examples of the blitter, just note that, because I know that some of you do not understand Italian, not like Cozy. So if you try the examples, know that the first 2 or 3, I can't remember, yeah, nothing happens on the screen, okay? That is all. That's why I'm mentioning it. So thank you very much. Thank you. Bye-bye.